Oh, you don't have to. Just don't bother. Yeah,
Huh?
it's okay.
Okay. So welcome to this seminar. This afternoon, we are very happy to have Professor Saurabh Amin from MIT, Department of Civil and Environmental Engineering, with us. And a little bit background. Saurabh is Robert N. Noyes Career Development Associate Professor at MIT, and he is also affiliated with the Institute of Data Systems and Society and the Operations Research Center at MIT, in addition to the Department of Civil and Environmental Engineering. His research focuses on the design of network inspection and control algorithms for infrastructure systems resilience. And he focuses on the effect of security attacks and natural events on the survivability of cyber physical systems and designs incentive mechanisms to reduce network risks. So Saurabh got his PhD from UC Berkeley in 2011, and he's a recipient of NSF CPS Forces Frontier Project, NSF Career Award, Google Faculty Research Award, DoD Science of Security Program, and Civil Energy Institute grant. Okay, so let's welcome Saurabh to give this presentation.
Thank you. Thank you very much, and thank you for the opportunity. And it's very nice to come here. So first, I should congratulate you to have a very new name, Civil and Urban Engineering, and I think it's very inspiring for a lot of other civil and environmental engineering department to have the urban spin on it. And so in that sense, you are the leader in trying to view our discipline in a new light. And also, I'm happy to see many nice things which Lee told me about the campus and about the transportation and systems activity here at MIT. Here at here at NYU, I'm sorry. So now, I have some work in transportation, but I figured Lee is much more capable in summarizing the work in transportation. So I decided to actually give a complementary perspective, and it is at the interface of some analytics-driven techniques as well as machine learning techniques and optimization, large-scale optimization towards infrastructure resilience. So most of my work is about non-nominal situations in large-scale critical infrastructures. And what I do in my work is to try to draw inspiration from three domains: transportation, water, and electricity, and try to think about ways, technological ways to improve the resilience of these infrastructures through sensing and control means. Okay, so this is a joint work with Mathieu Dahan, who is graduating at MIT from MIT and joining Georgia Tech Industrial and Systems Engineering Department. Georgia Perakis from MIT Sloan School, and Lina Sela, who is a former postdoc, now a professor in UT Austin. So let me start. Um, Maybe it's not on. Okay, so the motivation is that infrastructure systems are routinely subject to reliability and security failures. So we're used to thinking about natural disasters and the impact of hurricanes and earthquakes and other intense events on our infrastructures, typically leading to correlated failures and large-scale failures in these systems. More recently, there has been also evidence. Sorry about this.
Does that keyboard work?
No, it should be pressing. Yeah, just press down.
Okay. So more recently, there has been instances of malicious entities, which are cyber attackers or nation states or computer hackers, trying to gain access to one or more channels in these systems to do physical damage. Okay, and so in the context of pipeline systems, for example, there have been numerous incidences, most notably this Turkish pipeline cyber attack, which was recently in news, where some hackers gained access to the pipeline, and the sensors were not even able to detect this attack. Okay, so let's say if we want to kind of view this response to these events, reliability and security events, as a control system, this is a very slow control system, right? Where you could imagine that there are alerts which are generated by sensors or human customers, to the control center operator who is remotely sitting and trying to gain as much situation awareness about the network as possible, and then trying to instantiate decisions which are either automatic or driven by repair and response personnel to respond and contain the damage which is provided by this infrastructure. So the key message I wanted to convey is that currently this state of alert collection and decision making in non-nominal disaster prone situations is very slow. Okay, and there is a lot of opportunities for sensing, control, and optimization to improve this loop, right, both in terms of its effectiveness and timeliness. Okay. So there are certain challenges which are associated with the response operations at the current time. So the first challenge is this diagnostic uncertainty. We do not know who has caused these events, whether it is a natural event of this kind or the other kind, what kind of damage has happened, where the damage is happening in the network. There could be hundreds or millions of components in this network. And typically, the resource limitations also constrain the response operations because we do not have enough sensors to deploy, right? We do not have enough response and repair personnel to respond to these failures in a timely manner, right? And a side result of these two challenges is the fact that although the utilities and infrastructure owners currently have a lot of data which they can use for nominal and day-to-day situations, but they do not have a principled approach to use the data for decision making under non-nominal situations. Okay, so there is this gap between analytics methods and decision problems in disaster prone situations, right? So as a result, for example, in the natural gas systems, you would find that in a big city like New York, there will be inspection of these natural gas pipelines once every couple of years. Okay, and they'll be only responding through response operations only when an alert is generated. And in some cases, this alert will already be a disaster, right? Like blowing up a part of the city by the time the people are able to respond to it. Okay. So as a consequence of these limitations, what we have is that from the cost perspective, there is a huge repair cost which the utility faces in order to respond and address these failures, and let alone the lost revenue and the other kind of customer inconveniences which people face, right? So this is the data from Stephen Link's thesis, who completed his LGO thesis with PG&E recently. Okay. And in many cases, as I noted before, minor incidents evolve to become major disruptions. So it's similar to cascading failures in transportation, but except that these kind of failures can be also having direct threat to human safety, right, if something blows up, right? And as I said, more recently, there has been confirmed incidents and increased risk of physical and remote access to components by malicious adversaries, which can range from disgruntled employees or even nation states, okay, and sophisticated computer hackers. Okay, so these are the consequences, and these particular limitations and consequences raise a research agenda. Okay, raise a research agenda of the following kind, that how about utilizing the operational data which is currently available and archived by many service utilities, as well as public data from customers from emergency alerts, and combine these data into a predictive analytics framework where one is able to use machine learning techniques in order to generate alerts or information that are directly useful for decision making purposes, in particular to try to operate or respond to incidents and inspect the network in order to gain more situational awareness. And so on one hand, there's a use of machine learning techniques, and on the other hand, there's an opportunity to use tools from optimization, large-scale optimization, as well as game theoretic techniques to kind of design these algorithms which will influence the inspection and response operations. So the key agenda which I want to convey here is that there are new opportunities and challenges in using machine learning, optimization, and game theory tools to practically improve service operations for large-scale infrastructures. Okay, so that is the key message I'm trying to convey in this talk. Okay. So please feel free to interrupt me and ask me questions rather than putting all your questions at the end. Okay, so please raise your hand. I'm very fine to kind of stop and answer questions in between. Okay, so let me try to situate this particular agenda in terms of the timeline. Okay. So this is the x-axis is the timeline. And let's say that you have a large infrastructure. In the case of, let's say, natural gas pipelines, you have various kind of failure events. You have infrastructure deterioration, you have big natural disasters or strategic attacks, right? And typically, as an infrastructure utility, what you have as a part of risk assessment is vulnerability of various components, right? You will have some components which will be more or less critical, that if they are taken down, they will have severe consequences, right? So how about using this outcome of vulnerability assessment, which very service utilities already have, to try to design network monitoring strategies which can increase your chances to detect the failure, even when these failures are of strategic nature, malicious nature. Okay? So this is about trying to design sensing strategies or monitoring strategies using available sensors in order to maximize the chance of detection before any failure event happens. Now, let's say that a failure event does happen. One or different kinds of failure event could happen, and it could affect multiple components. You collect new data. You have new data because these failure events are going to directly impact the physical behavior of the system, right? Which will be captured by, hopefully captured by the sensors. And now you have this diagnostic information which you can use in order to build predictive models, right, which will tell you something about the nature and the location of failures in a large infrastructure network. And then to inform the response operation team, right, or teams, in order to gain further knowledge about these failures and repair these failures in a timely manner. Right? So this is the analytics-driven response operations, and this is in some sense vulnerability-driven network monitoring. Okay? So you see the duality between data and decision. So this is data part, and these are the decision part. On the other hand, that is the some kind of pre-decision available in terms of vulnerability, and then that influences the network monitoring itself. Okay? So the two applications I'm going to discuss are about disaster response and security, but noting that the same kind of ideas would generalize to humanitarian systems as well. Okay. So let me go through the first part of my talk, and this is about integrating predictive diagnostics and response operations. Okay. Now, the motivation is a very age-old software called Dash, which is Dynamic Automated Seismic Hazard, which is used by many of the utilities which are in earthquake-prone zones. Okay. So this is actually data of a Northern California region where there is a utility, prominent utility, who actually faced this 2014 Napa earthquake, and it used Dash, right? So Dash is actually a fully calibrated, geological software. And what it did is that it actually sent the utility personnel to wrong areas. So it predicted failures in some regions, but the actual failures were in some other regions. And so it resulted in wasteful effort on the part of inspection operation teams. Okay? So from a scratch, let's say if you were to kind of have an alternative to this Dash system, the key features we need to account for are first diagnostic uncertainty about the failures, the time constraints faced by the leak survey crews because there's only certain number of hours they can work every day, and spatial distances between the regions because they have to lift their equipment and go from one point to another. Okay, so this has an aspect of routing problems for those of you who are familiar with traveling salesmen like problems in transportation. Okay, and that's why it is of interest to this community as well, I hope. So the key trade-off which we want to capture is that if you are having an inspection team in a region, right, whether you should keep exploring and finding more failures within that region given the time budget you have, or you should abandon inspecting that failure and go to other regions to also cover part of the other regions. Okay. So, and the problem is how to optimize the scheduling of monitoring resources, which is similar to, as I said, classical routing problems. In this case, it is leak survey crews under this diagnostic uncertainty. All right. So this is actually the region of that Northern California region. And this is the earthquake which I just created for you. Okay. So these are the various zones which the utility needs to inspect, and these are called plats. These are 100 by 100 yards regions. And you have to inspect all this in fastest time possible for failures. Okay. So what happened after the 2014 Napa earthquake is that the utility was ultimately able to take care of 59 service regions with identified failures or damages. Okay. But what happened in reality was that after 6 days of inspection effort, The number of regions surveyed were only 75 out of many hundreds. And with a fraction of leaks actually detected, out of those 59, only 22 regions were identified as one with failures. And there's a wasteful inspection effort of 53 regions where you could not find any inspection, any failure, right? So this is actually a wasteful inspection. So there's a large increase in inspection cost and significant restoration delays because the inspection operation is conducted in a very ad hoc manner. Okay, they have emergency service centers, they have drills, they have military style practices in terms of responding to the failures, but it is uninformed. Okay, so the key limitation is that the data is there, right, but it is fed into a legacy system, right, and it has some kind of connection with a rule-based dispatch, but this is typically somebody in the control systems of operation center with few years of experience and having rules of thumbs to dispatch the inspection crews and generating an inspection strategy. So the alternative which we are proposing is, and of course this has limitation in terms of poor damage assessment and inefficient dispatch. So the alternative which we are proposing is to come up with a predictive model, right, using the data which we already have available, but instead of using Dash, use state-of-the-art machine learning tools which every one of us is familiar with, and then inform the output of this and use this output of this predictive model to formulate and solve a large-scale stochastic optimization problem, which is similar to a stochastic traveling salesman's problem. Okay. So let me first try to tell you about the predictive model. So this is actually 475 regions that utility is concerned with, and remember that in the Napa earthquake we had 59 leaks. So what we have the data for this Napa earthquake, right? And what we have is the data which is used by the Dash software already. So there's some earthquake-specific, geological, soil-specific data which is available, which the Dash software already uses, right? There is additional data which we gathered in terms of the network topology, the infrastructure, in this case pipelines, right? Whether it's plastic or whether it is steel, what is the length, what is the configuration. So all that is available. And in addition, there is data available of customer calls, alerts, right, through Twitter feeds and through did you experience kind of reports which can be collected through social media immediately after the earthquake event. Okay, so we collected all this data. And what we want to do is that we utilize this data to predict the number of leaks or failures per region. Okay, so that's a classical prediction problem. There's a training phase to it, and testing phase, and then predict. Okay, and one of the things which we had to do, however, is that we need to kind of account for the imbalance of cost between false alert and misdetection. So as a utility, you would expect that if the actual number of leak is, let's say, higher, and if you predict that there is no leak, then you will be more costly for you. So misdetection is more costly to you than false alarm, right? So you actually discuss with the utility personnel to kind of come up with these weights in before training this model. And then you try, the master student try a bunch of different kind of algorithms. And so we tried that. And so it now happens that this logistic regression gives the best performance. Okay. Now this has to be evaluated against the testing data, and we do not have many earthquakes thankfully hitting the region. So what we do is that we create a test data out of the data we already have to evaluate the performance of our model. And in reality, if you have new earthquakes, of course you should evaluate the model performance on the new earthquakes as well. So what we find is that out of the regions, in terms of one-to-one comparison between the Dash model and our model, our approach identified 24 regions for inspection as opposed to 18, for example. And the number of regions incorrectly chosen for survey was 12 of the same order as Dash, right? But the number of regions correctly identified was about 80% as opposed to 47% of regions correctly identified by Dash. All these are valid comparisons or valid advantages, but the key advantage is this one, that a machine learning model is able to generate results in terms of the prediction of the failure rate in different regions just 2 hours after the event happens, as opposed to Dash, which requires 2 full days to generate all these scenarios of earthquake prioritization and shaking of the ground, etc., and try to predict. Okay, so there's a full-blown exercise in calibrating and operationalizing Dash after the event, which is a waste of time. Okay. So that is the predictive model. And now we are in the phase of optimization. So what we have from the predictive model is the probability of failure generated or predicted for each of the regions. Right? Now we turn into a stochastic optimization problem, which I hope will be of interest to those of you who are interested in routing problems in transportation. Okay, so in this problem, it is going to be about orienteering and probing. Is anybody familiar with orienteering problems in transport? Okay, good. So I hope that you know. And for those of you who are not familiar with, I'll introduce you. Okay, so please don't worry. Okay, so what the setup is? So the setup is similar to a routing problem. There is a control center which is a base station L0, and then there is a number of regions which you need to visit. Okay, and each region is having a bunch of components that you need to inspect in order to find a failure in there or not. Okay, so each region has two parameters. One is the value, the monetary value of finding a leak in a timely manner in that region, V1, which we can get based on the criticality of the components there, with this hospital or prison or a critical facility, etc. And there's a probability pi, which is an output of a logistic regression model. Okay, probability of finding the leak. And there's a travel time between different regions, right? So you can see that these are nodes of a transportation network, but each node has sufficient richness in the sense that you need to inspect or probe each node for finding a failure. Okay, so that's what this is. So each region contains a failure with probability pi, and we have no other information about the probability distribution of the failure apart from the fact that the logistic regression told us that it is pi, right? So what we do, we assume that it's uniformly distributed. It's a uniform prior, right? Non-informative prior in that region. Okay.
So
Yeah.
there's no consideration of the time of the failure. No? So they all happen just after the earthquake.
Yeah. So what you do is that after the earthquake, you collect the data, you observe the alerts or the emergency personnel call for, let's say, 24 hours. And that time, the emergency control center gathers the crews and tries to kind of give them this information. So you have 24 hours or 48 hours of window before you are allowed to kind of send the inspection crews, because they won't be able to go immediately after because of, let's say, access of transportation network, etc.
And also there is no information about the severity of the leak.
No, no. So the point is that the machine learning model in some cases, for example, is subject to the data where the customer calls are actually just freaked out. You know, the customer is just saying, oh, there's some smell of methane, but actually it's not any issue, right? So those kind of things affect the probability of correct prediction. Yes.
But if you have, for example, larger pipe than a smaller pipe.
Yeah. So
they both cracked. I mean, the severity might be different.
So that is captured in the as a feature of the logistic model, because now we also take into account the age of the pipeline, the diameter of the pipeline, and the material type of the pipeline, in addition to the depth of the pipeline, etc. Right. So those features are there in the predictive model of the failure.
Also, maybe the history of maintenance.
The last maintenance history is also there. Exactly. Yeah. So all those can be captured. Yeah. Yeah. That's good. Any other questions so far? Okay. So what we have now is that in that region, there are multiple locations which need to be inspected. And let's say that now there are a certain number of n locations which need to be inspected. And now we are ready to actually formulate our optimization problem. So what we have is the time budget. That's why it's an orienteering kind of constraint. A time budget, capital T, let's say 6 hours of inspection time each day. We have repair teams actions, which have the following available actions. So you start visiting a location and you keep on exploring that location more, which is called the probing location to find the failure, or you have an option to go to another location. Okay, and that's the orienteering part. And the key aspect here is that once if the inspection crew is trying to monitor a location, they will know whether there's a problem or not, right? So the uncertainty is realized as soon as you inspect a particular location. So mathematically speaking, this is a multi-stage stochastic optimization problem, right? It's a hard multi-stage stochastic optimization problem. And the goal is to find a reasonable policy which maximizes the expected value of the total number of failures you are able to catch, right? Given the time budget you have and given the constraints of traveling you have. Okay, so there is some literature which I'm not going to go through, but essentially what I want to convey is that although this is a multi-stage stochastic optimization problem, the computer science community has made a lot of advancements in recent years in designing approximation algorithms which with good approximation, with good optimality guarantees relative to the best solution, which is NP hard to compute. Okay, so there is some related work, and I can talk to you offline about the mapping of our problem with the related work, but I'll skip that for time reasons. So let's go to the solution approach. Okay, so in these kind of stochastic optimization problems, people who are familiar with dynamic programming, let's say, would actually think about adaptive policies. Adaptive policies means that once the uncertainty has realized, right, I am able to kind of use that realization of the uncertainty to decide my next decision step. Okay, that is in some sense a feedback control policy, if you will, right? But there's alternative to this, which is called as open loop policies, which are non-adaptive policies, which are not dependent on the realization of the uncertainty. And this is the class of policies which I'm going to be focusing on because of a couple of reasons. The first reason is that the typical adaptive policies from a computational viewpoint face the curse of dimensionality. Okay, very hard, blows up immediately fast as you increase the problem size. The second is that from a practical viewpoint, it is unclear whether the inspection crews will be able to take advantage of the realized uncertainty, because from a decision maker's viewpoint, you want to tell the inspection crews in the morning of the each day that you go visit this location, and that location. You don't want to be in a situation where the inspection crew is waiting for your decision on where next to go in the middle of the day. Right? So here is, so that's what I'll be focusing on. I'll be focusing on non-adaptive policies, and I'll be trying to explore or exploit the features of the problem, which is the expected value, the travel time between locations, and something called expected exploration time, right? So the expected time to explore a particular region, given the probability of failure in that region and given the number of components in that region. So let me try to explain to you performance of two previously known algorithms in this space, a greedy algorithm and an integer programming based solution. Okay. So a greedy algorithm is the one which says the following. It's a myopic algorithm that each localization set or each region, you decide the next region based on the one which is maximizing this ratio of the expected value divided by the travel time. So you would want to go to a region which has the higher expected value of reward, right? So you actually greedily choose a region to inspect based on the current region to inspect using this myopic policy. Right? Another policy is actually something which is reported in the literature, which is based on integer programming based approaches, which is called as the truncated knapsack. Okay, so bear with me as I explain to you the features of this policy. So you have a total inspection time t. Okay, this total inspection time t is going to be utilized for traveling to from one region to another, as well as inspecting different regions. Right, so that is the t travel and t explore. Right, so you decide some partitioning of the total time into t explore and t travel, and you impose in your routing policy that these constraints are met. Okay, the total travel time and the expected exploration time constraints are met. Note the word expected here. Okay. So there are previous works which have been published in computer science community about approximation algorithms to these class of problems. So notably, this truncated knapsack orienting problem is able to give order log t approximation with respect to the optimal adaptive policy, which we do not know and which we do not know even how to compute, and order 1 approximation with regard to the optimal non-adaptive policy, which we also do not know yet. Okay. So one would say that order 1 is fine. So the literature, the results in the literature is fine, but the catch here is that the constant can be very large. Okay, can be 500, can be 5,000, very large. So it doesn't make a practical sense even if you have an order 1 approximation, because what can happen is that let's say you have some exploration budget, and let's say that you are able to explore 3 regions, L1, L2, and L3. Right? Note that this particular constraint is in expectation. So what may happen for a particular realization that you have some extra time left, and you could have had one more region inspected, but you did not because you pre-decided to satisfy this hard constraint in expectation. Okay, so it's a waste of travel time resource, available time resource here in this known approach. Okay, so what we do, we actually try to take a original approach to try to find or gain a handle on a non-adaptive policy. So that is the focus of the next two slides, which will be a bit notational, but please bear with me. Okay, so the optimal non-adaptive policy which we want to kind of explore is of the following: that you explore a region, you continue to explore until you find the failure, right? Or you reach the end of that region. Once you find the failure, right, you go to the next one. Okay, so the only decision here is the order in which you visit different regions, because you already have decided your exploration strategy of that region. Okay, so that's what it is. We want to find an optimal ordering of regions that maximizes the expected reward, which is over the bunch of regions, the value, okay, expected value, vi times pi I, times the expected number of visited monitoring locations. Okay, we want to find, we want to kind of find an ordering which maximizes this particular objective function. Now, this objective function is very messy, nonlinear, combinatorial to evaluate objective function. Okay, so this is just saying that we have an analytical expression of the expected number of visited monitoring locations n I bar, but it's a mess even to evaluate it. Okay, because you have to evaluate the whole tree on what have you visited before and when did you in expectation stop, right, and move to the next region. So it's very hard to even compute. The good thing is that we have a way to recursively express this expected number of locations. So it's saying that the expected number of location visited in the ith region is the summation of two parts. One is the one where in the previous region, you happen to explore the whole region and you were only able to leave when you were not able to find the failure because the region was completed. And the first part, the first term, is corresponding to the fact that you found the failure somewhere in between and left immediately after. Okay, so it's a recursive expression which can be tractably evaluated. Okay, and now we have these two quantities. We have what is your objective which you want to maximize, and you have this recursive expression for this term n I bar, which is the expected number of monitoring locations you visit for the ith location. Okay, so the gist of the story is that it is possible to solve this nonlinear problem into reformulate it into a large scale mixed integer linear program. Okay, mixed integer linear program, and also have some flavors of the traveling salesman's problem. So for those of you who are familiar with traveling salesman problem, we know that we need to eliminate something called subtours. We need to eliminate we need to impose those subtour elimination constraints. So those are those classical constraints. And there are this bunch of constraints which are coming from the objective function, which is here, right? Maximizing the expected profit which I get or expected value which I get in getting as much failures inspected as possible. And this particular constraint forms one of the probing constraints as an integer linear constraint. Okay, and then you have these y variables instead of the original z variables here, which are saying that you also need to account for all the locations which you visited before. So that is the kind of a tour constraint, right? That is the fact that you need to be arriving at a particular location from some other locations, noting the the distance between the two locations. So those are those. So this is a large scale mixed integer program. Okay, and commercial solvers like Gurobi are smart enough to solve these large scale integer programs. So they can actually do it with a laptop implementation for 60 regions. And in reality, you can actually use more sophisticated algorithms for traveling salesmen's problems to accelerate this a little bit. But we already get some improvement. Let's say we, over the greedy algorithm, we get up to 5% improvement for this integer programming based solution, which I just proposed. And the knapsack is over, let's say, around the same, some kind of same order of improvement. But note that the greedy and the knapsack have some instances which give you bad performance. So our algorithm provides up to 70% improvement for some of the bad instances where greedy and the knapsack based approaches do not perform well. Okay, now there's one point which I want to make here is that you see, when you are inspecting a region, you would imagine whether I should go or visit a region where I'll be having a larger value or larger probability of finding a failure, right? So the key insight from here is that the the algorithm prefers to visit locations which have high probability of failure in comparison to the high value failures. Because if you were to visit high probability failures first, high probability regions first, you will save some time by finding the failure with higher likelihood earlier on and leaving that particular region to visit other regions. Okay. So it saves you some time. And the leading term for, let's say, visiting ith region also depends on the probability of finding failures in all the previous regions which I visited, right? So a probability of failure of a given region is going to affect my selection procedure for the subsequent regions, okay? So that is actually one nice insight which we also got from this thing.
So,
Yeah.
so I mean, you have one crew, no? One crew is
Yes.
going. But if you imagine if you have multiple crews,
So that is something which is work in progress. Yeah.
you can basically cluster.
Yes. Yeah. So there is actually algorithms in the TSP style problems or this vehicle routing problems where you actually associate one crew with a bunch of nodes, and then you kind of partition the jobs across these nodes. And then of course it's an approximate solution, but there's ways to kind of bound the optimality of these solutions. Yeah.
And when you build those regions, basically you want to maximize whatever value you have within that region.
Yeah. 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 And again, it's
But
so again, it's a trade-off between going from region to region, right, and trying to actually visit regions which are having high value and high probability, right? So there is this kind of trade-offs which you have to get, right?
do you take advantage of the underlying graph? Because
Yeah. So exactly. So in the multi resource or multi inspection crew problems, the graph structure is going to be useful for partitioning the network and assigning the jobs to multiple inspection crews. Yeah. Yeah. So it's similar to these pickup problems or delivery problems in transportation and logistics. Okay, so that's why I thought it is it's interesting to this community. Okay, so right now the summary is that you have a failure prediction model, and then we propose a new stochastic orienteering and probing problem, and deal with the class of non-adaptive algorithms which approximation guarantees. And as Khan said, we are currently working on trying to extend this formulation for multiple repair teams and multiple leaks per region. And also from a control viewpoint, it is of use to kind of think about the following strategy: that suppose you actually get some inspection done on the first day, then how to operationalize the crews on the next day, right? So can this information which you got in inspecting the first day of operations be used to retrain your model and and inform the inspection on the subsequent days, right? So this feedback loop is also something which is of importance. Yep.
Could you talk a little bit more about how you implement the multiple leaks per region? Because right now you said that it's once you find a leak, you're done. So is there a probability of finding a second leak and then on, or?
Yeah, so in some sense, if you have, so there are various aspects associated with, so first of all, this particular approach can be used to post-analyze the performance of the same algorithm if there were multiple leaks per region, and there's some guarantees that can be done. In some sense, the aspect of multiple leaks per region is simpler, because what you would do is that you would always expect to find one more leak, right? After even you have found the leak. So that one of the approaches would be to inspect the full region regardless, right? So this aspect of leaving the region in between somehow is out of the picture, right?
Okay.
Yeah.
So, but that would increase your the
The time of
inspection,
yeah,
right?
yeah, yeah. Any other questions? Okay.
I mean, I think also for the predictive model, you even have to look not for next day, but the next inspection. Because the moment you go there, you know that if the prediction is correct or not.
So that is the practical aspect of the thing. So if the inspection crews are agile enough to kind of have the control center's guidance in the middle of the day, then it is fine. But in our discussion with many of the utilities, we find that they try to fix the plan for the whole day. Yeah.
Like airlines.
Yeah. Yeah.
But the thing is, there's also time aspect. So some crews will reach their destination very quickly
Yeah.
because it will be close to the garage, whatever.
Uh-huh.
So they can immediately
Go.
report back.
Yeah.
There might be some
That is fine. Yeah, so there is a similar project in terms of, you see, there is, in terms of actually reporting back, if you were to take if we were to actually take advantage of, let's say, newer sensing technologies such as UAS, unmanned aerial systems, where you have a base station and you actually locally kind of quickly survey the area and report back and update your model. So those kind of approaches are better suited for faster mobile sensing techniques.
Because running this doesn't take too long.
Yeah, right. So there is another kind of sister project which I'll summarize, time permitting, in a couple of slides, where this kind of more dynamic update is something which we have been doing. Yeah. So I have 15 minutes. So I want to kind of give you a high level flavor of the second project. I don't intend to complete all the slides, but this is about game theory. Okay, this is about game theory in the presence of strategic attacks, monitoring in the presence of strategic attacks. So let me try to give you a very high level picture, and leave 5 minutes before, please alert me so that I can wind up the presentation. Okay, so remember that we have some critical components, and let's say that we have access to mobile sensors, like, mobile detectors. So in typical gas utility business, there are these Picaro leak detectors who have come. So there is methane sensors mounted on a car who can actually survey an urban region, and of course there are UAS as well. So this mobile and flexible positioning. And the problem here is that, let's say that if you have a fixed number of these UAS and Picaro sensors, methane sensor mounted cars, how to strategically position them in a large scale network, right, in order to maximize the chance of detecting an adversarial failure who will target components in a strategic manner in order to avoid detection. Okay, so think about this Turkish pipeline attack, which I initially motivated the presentation from. So the key features are that there is a operator attacker interaction, and you have multiple disruptions that can be conducted by an attacker in a strategic manner. And one of the things which actually comes about naturally in these class of problems is the idea of randomization. Let's say that the police patrol or the canine units in an airport, or even the kind of inspectors in a gas pipeline network, they have the strategy of randomly sampling the network. Okay, so this the randomization is actually a practical strategy which they employ in responding to certain threats. Okay. So there is actually, the key features are that you have a generic detection model, which we want to account for, and we want to position these resources in a strategic manner in order to maximize, as I said, the detection probability. And essentially, it's again a large-scale optimization problem, but this optimization problem is influenced by the strategies, game theoretic strategies of attacker and defender. Okay, so that is actually what is called as mathematical program with equilibrium constraints. So let me just briefly summarize what the attacker-defender model is, right? So you have a bunch of components, right? And all these components, these edges E1 to E10, are strategic, in the sense that they can be vulnerable to actions of an adversary. And what you have is that a bunch of nodes where you can possibly place your detectors, for example, your methane leak detector, which is the formation of the operator strategy. Okay, and what you have is some kind of ability of detection of the operator, that if the operator were to place his sensor at a particular node, he can detect the failures in some components. Okay, so it doesn't need to be contiguous. You could have a vision sensor, right? You could actually have an obstruction of a tree, right? And you can only monitor some components which are in the field of view. Okay, so now there is an attacker-defender game. So this attacker is going to be able to attack subsets of these components, right? So all possible combinations of subsets of these components which are of a given size, let's say B1, so that's a sensor. So B1 is the number of sensors, and B2 is the number of attack resources. So the defender or the operator can place subsets, places sensors on subsets of nodes, so that so long as the size of the sensors is smaller than B1, right? And the attacker can target subsets of edges, right, so long as the size of this attack is smaller than B2. Right? So this particular game is a generalization of many hide and seek, search games, inspection games in the operations research literature. But the key feature of this game is that the attacker and the defender have multiple resources and they can simultaneously act in a strategic manner. So one player does not get to know the actions of the other player before acting. Okay, so that is the key point here. So there are actually some aspects of the game, but let me try to summarize in the interest of time what the strategy is. Okay. So there is something. I will skip this for the interest of time. So the okay. So let me try to tell you what the strategy is. So suppose that you are a defender, okay, and you have to kind of place a limited number of sensors on a large network. Where would you place the sensors in a randomized manner? So the key insight here is that we place the sensors on subsets of what is called as a minimum set cover. Okay, a minimum set cover is a combinatorial object which covers the entire network. You want to kind of select positions of locations which actually have largest chance of covering the whole network. Right? You want to detect as many attacks as possible, and the attacker is going to target his resources on edges which are far away from each other. Okay, in the sense that if the attacker wants to if attacker happens to cluster his resources nearby, right, or target edges nearby, then it will be a wasteful effort because the detector or the operator is going to be easily able to detect these attacks, right? So the attacker wants to spread across the whole network, and these are actually notions which are called minimum set cover and maximum set packing problems. Okay, these are combinatorial objects, again defined in graph theory and in combinatorial optimization, which actually captures likely strategy over which the attacker and the defender should randomize their actions. So the key contribution here in this work is that we actually identify reasonable randomization strategies based on these combinatorial objects and show that they are near optimal. Near optimal in the sense of equilibrium of the game, that the attacker and the defender, if engaged in this strategic play, are not going to be improving given what they are facing, right? So it is in that sense a Nash equilibrium of this large scale game. Another thing to note here is that most of the current algorithms for solving large scale games would fail for the class of problems which we are dealing here. So although these set cover and set packing problems are combinatorial objects, modern integer programming solvers are again able to solve this in an efficient manner, in a scalable manner. And this approach of randomization gives you a good approximation guarantee against the Nash equilibrium at actual Nash equilibrium, which we do not know how to compute. Okay, so I'll skip all this in the interest of time. So essentially, this is what this is. So this is a large scale network, let's say of 1,000 nodes and 1,000 pipes. And what the operator does is that he has some resources, and these circles, the circles are the minimum set cover, and the operator is going to sample based on the number of sensors he has, randomly select nodes from this set cover and try to monitor them, right? And the attacker, the best strategy for the attacker is to use the so-called maximum set packing, right, to spread his attack as far as possible, right? Okay. So what we find, yes.
So, how do you deal with like non-uniqueness?
So that's a very good point. So this is actually this guarantee. So the point is that this approach of MSC based sensing, minimum set cover based sensing, does not assume uniqueness, right? So it is guaranteed against all attacks, all Nash equilibria, and moreover, it in some sense it does not even assume rational behavior on the part of adversaries. It's the worst case. It's in that sense it's a robust solution, right? And furthermore, because of the property of the network, you do not actually need the exact knowledge of the attacker resources also, right? So there are very nice properties which actually this particular solution provides in terms of robustness guarantees, right? So I'll actually skip all that. So essentially what we have is that as an output of this, we have for a bunch of networks, we can actually solve for this MSC based strategy, and we can provide guarantees, optimality guarantees, that if somebody were able to solve this large scale game and come up with the minimum number of sensors which is needed, we won't be actually far away from that unknown number by a certain margin. So we have an optimality gap. So for 6 out of 13 networks, we are able to compute an exact solution, a provably exact solution. And for the remaining networks, we have a small optimality gap of, let's say, about 6 to 7%, right? So we are off then the true minimum number of sensors or detectors which are needed to achieve a certain detection guarantee by no more than 7%. Okay. And the key here is that the MSC, the minimum set cover and maximum set packing, they can be computed for even very large city scale networks of the order of few minutes. Okay. On the other hand, if I were to actually solve for the state of the art algorithms, using state of the art algorithms to solve these large scale games, right, I do not have currently even a way to store these particular games on a computer, the linear programming versions of the game on a computer. So it's impossible to compute an exact Nash equilibrium using state of the art algorithms. So the key idea, there is a lot of mathematical details which are there in the paper which we upload online, but it is an aspect of submodularity. So there's a field in optimization in sensing called submodular optimization. So we use property of submodularity of the detection problem. We also use game theoretic arguments and the properties of the minimum set cover and set packing to derive these guarantees on our sensing approaches. So I'm sorry that I did not have the time to go through the details of this second part. But really the hope is that this aspect of proactively deploying sensing resources in anticipation of malicious and random events, and also to use analytics driven techniques to kind of proactively respond to these events in a timely manner after the events happen, is a rich and exciting agenda. Okay, that's what I wanted to convey. And there are many kind of critical situations of strategic importance, of national importance, which are available, which are out there for this approach to be applied. Okay. Yes.
By using MSA and SP, does it mean that the payoff for covering homogeneous across the network?
Yeah, so we have assumed in this, that's a good point. In this particular model, we are assuming that we do not have the ability to distinguish between the criticality of various components, in the sense that the game is played on components which are of similar criticality levels. Now, as a follow-up of this work, we have extended part of this work to a network of heterogeneous component criticalities, where the notion of these strategies would change a little bit, because now the operator is going to, in some cases, prioritize inspecting more critical components and lose some part of the network completely unmonitored, given the attacker's action. Yeah, that's a good question. Okay, so last couple of slides. So going back to this discussion which Khan raised about the more proactive kind of integration of diagnostic information. So there is some work which we have been doing on use of UAS, unmanned aerial systems, to assist inspection operations. And in this case, we are working with Houston Flood Control District, which has actually faced a heavy flooding event in the aftermath of Hurricane Harvey a couple of years ago. And in that case, this infrastructure network is not a pipeline network, but a drainage network, okay? The network of drainage network canals in the greater Houston metropolitan area. And these red dots over there are flood sensors. So these Houston Flood Control District, and even nationwide. So a few weeks ago, or last week even, you may have seen this article on New York Times, where certain parts of the country were flooded because of this rains, right? Unexpected rains. And in the New York Times article, there is this very nice dynamic of flood sensors where the flood levels were going up and down. So similar kind of flood sensors are available throughout the country, and of course in the Houston area. And these flood sensors actually can be used to give alerts that if the water level at a particular location is above a certain threshold, then that particular region needs to be inspected quickly, because the road network and the other kind of drainage network in the vicinity is subject to flooding induced failures. Right. So currently, the inspection operations of this Houston Flood Control District does not account for this flood sensor alerts in doing their inspection operations, or even routing their emergency response crews. So what we are proposing is that if we can identify these regions based on the alert levels of from the flood sensors, we can then dispatch the inspection crews to particular access point, and this would again require finding out which transportation links are accessible, whether they are flooded or not. And once you find that it's flooded, you actually go to an access point and then launch a UAS to kind of inspect the network locally, given that you're not able to kind of send the inspection personnel right there near the location to inspect, okay, because of bad conditions, okay. So this combination of repair vehicles and response vehicles with mobility-driven inspection solutions is an exciting agenda, combined, of course, with the integration of the infrastructure sensors, in this particular case, flood sensors. So again, it raises a good possibility of combining predictive algorithms and routing optimization type algorithms. Okay. So what we find here is that integrating these new sensors, flood sensors and UAS, always increases the rate of the total cost of failures, which you are able to find early on, right? So this is days after the event, days after the Hurricane Harvey. So this is real data. And this is actually, in some sense, the performance of their current inspection strategy, even assuming that they are going to do it in an optimized manner, right? And this is saying that if you were to kind of integrate the predictive information, either from the flood sensors or from the UAS, which are mobile sensors, or both, right, you are able to catch higher criticality failures or more costly failures much earlier on in comparison to a very delayed cost of identifying, first identifying and then responding to these failures. Okay, and again, it's a combination of predictive models and deriving, for example, scalable integer programming based routing strategies, which admit the output of the predictive models and suggest strategies which are reasonable. Okay. So this is the agenda. So I hope that before the event, I try to convey some aspect of strategic modeling. And after the event, I try to convey some aspect of data-driven or predictive analytics-driven optimization. And there are certain other stories which are of similar flavor. But in the interest of time, I'll skip discussing more about that. And just as a final note, the collaborators in this endeavor are PG&E, Houston Flood Control District, and support by Lincoln Labs Humanitarian Assistance and Disaster Relief Systems Group. Thank you.
I think we have time for 2 or 3 questions.
For the TSP, you're solving it as a imagery program, but I mean, you mentioned the scale was applied to like 60.
Yes.
So,
Yeah.
I mean, even then, it's pretty sizable, right?
It is pretty, but you see the point. Surprisingly, Gurobi and its sister implementations are surprisingly very, So the point is that when we say NP hard, I mean, in the point, the point is that in many of the current optimization implementation solvers, you get reasonable, yeah. I mean, so then why care about NP hardness? I mean, if you're able to, yeah. So yeah.
But then the reviewers will get criticizing. They'll say,
The things are changing, right? So the things are, I mean, yes, I mean, there is a group of optimization people who have much hope in the power of large-scale mixed integer solvers in the current time. And yeah, I mean, I agree with the reviewers, potential reviewers, that still it matters. But what matters is what is the kind of scale of problems which we are able to solve.
So the way you use the probabilistic approach for the Nash equilibrium problem.
Yeah.
So you say it's a robust solution, so you get the worst
Yeah.
case, basically. But do you generate them randomly?
Right. So it's in the main idea, and this is a kind of theoretical guarantee that for large networks and limited resources, a pure strategy, means deterministic strategy, is never going to be optimal, because if you were to be playing deterministic sensing, right, the attacker would anticipate that this particular region is monitored and he will target this region. And similarly, if you were to monitor this region, then they'll target some other region. So it's inherently the aspect of randomized or mixed strategy is a result, right? That you always can do better by using mixed strategies. And this mixed strategy, the claim is that you can actually operationalize in a day-to-day basis, in the following sense: that let's say that if you are facing a threat of contamination or threat of an adversarial attack, then each day you actually sample from that mixed strategy and make a plan for inspecting some regions on that day. And the next day you generate another sample from that distribution and you go on, right? So that's the way to operationalize this randomness. Yeah.
More questions? Okay, then let's thank Saurabh again.
Thank you.